This is a slide we're going to discuss today. I mean, this is a set of slides we're going to discuss today. You probably have them. I uploaded them before this week. There won't be any proofs today, which is good for this late hour. We're going to discuss with you extrema problems, how to find different extrema for the functions. So normally this starts with a bunch of the definitions. That's all of the definitions which are relevant to the extrema, which we need to know. Right, so basically, thank you. Basically, on this slide, there are two definitions about maximum and minimum. There are two types of maximum and minimum. One of them is called local, max and min. It's right here. So it's the point where function dominates neighboring values, if it's max, or it's the point where the function is lower than every neighboring point, if it's min. But it's irrelevant what are the values of the function in general, in the global perspective. On the other hand, absolute max or global max or absolute mean or global mean, it's the one which is relevant to some domain. So it's actually a very good sign or very good thing you can use to distinguish problems. When a question about the max or mean has a domain in it, it's certainly max, global max or global mean. If it doesn't have a domain, it's about local mean or local max. That's the first four on this definition. The last two, stationary and saddle point. Well, stationary is the one where the gradient is 0. And a saddle one, it's a stationary point with the extra condition that f is neither local max or at this point is neither local max and local mean. Right. Let's just flick to the next slide. That's right. That's the main result which we have to know in relation to the max and min. It's a main test. The first test, it's not always sufficient test, but most of the time it's a good test. Most of the time you can just use this test and nothing else. It tells you when you can expect local max or local mean at some point. So if you have a local max or local mean, the point will be one of three, which is listed here. It's either stationary, which means that the gradient is 0, or it is a boundary point, or the function is not differentiable there. So basically, when you're looking for the local max or local mean, or as a matter of fact, when you look for the global max and global mean as well, one of the first steps will be just finding all of the points where one of these three conditions is satisfied. One of these three conditions is satisfied. Either function is not differentiable, boundary points require special analysis, and the stationary points where the gradient is 0. Yeah, and that's another piece of a definition. Critical points are those points where one of these three is true. To tell you the truth, sometimes I'm losing myself in all of these definitions. Critical points, stationary points. Yeah, if it happens to you, don't get upset. It happens to me all the time. But right now I'm very clear on this. I mean, I just read the slide. Now I'm really perfect. I know everything. But in a few days I'll forget it unless I look at the slide. So just take it easy with this. So I have one example. Well, Jonathan Kress put together one example. It's a very typical example. It's the easiest example you can have. It's the easiest example you will see in the tutorial questions. It's the example how to find the global max or absolute max and global mean or absolute mean for a function on a domain. You see, domain omega is given here, and that's one of the main signs that we're talking about the global max or global mean. We need the value of the function, the max value of my function across this domain, and the mean value of my function across this domain. We do have such a value because function is continuous and the domain is compact. Today there was one student came to me to discuss the writing assignment, and that's the theorem we eventually realized was a helpful point there. The theorem is that every continuous function attains its max and mean, and this is a continuous function. So it has max, it has mean point across this triangle, across this omega, and we need to identify that. So what we normally say, or the way we normally think about this question is this. max happens either it happens at the stationary. Was it stationary? No, it was a critical. Or you forgot it. You see from the last slide. It happens at the critical point. That's the result from the last slide. So we need to see all of this. We need to see these three classes of points which constitute the critical points. First class is stationary points, gradient 0. Second class, boundary points. Third class, non-differentiable points. Well, third class is 0, empty here. Function is differentiable everywhere. It's an elementary function. So we don't have to consider the third class. But the first two classes, we do have to consider. The easiest one is the stationary point. That's what we start with, the gradient. That's what is said here. First class and second one, we have to find out those classes. The third class is empty. Function is differentiable. So for the first class, stationary points, we just solve a few equations. We compute the gradient. That's the computation. That's the value for the gradient right in here. Two partial derivatives, x and y. We equate them to 0. And you solve it in any way you like. Here, obviously, what is done is this. The first component, after equating the first component to 0, the equation is solved for y. Actually, both of them solved for y. This is the solution for, no, second one solved for x right in here. So first component equation solved for y. Second component equation is solved for x. Yeah, and then you substitute one into the other. You end up with the equation of this type. Fourth equation, x is factored out, and you have two trivial solutions. You have two solutions for x, 0 and -1 from the bracket. You substitute back for y, and that's the points, 0, 0, and 1, and -1, -1. It's a -1, 1. They are on the graph here. So these are my two critical points where max and mean may possibly happen. Values of my function at these points are here, 0 and 1. And at this stage, we just stop this line of investigation and we move on to the second part, boundary points. Because normally what happens is that you just find all of the possible candidates for max and mean in these three classes. In the first class, which is stationary point, we found them, 2 points. Second class, boundary points. You find all of the candidates in that class. Then you find all the candidates in the third class, which is empty in this case. And then you just run across these candidates and choose the max and choose the mean. Because you have finite number of candidates, it's the easiest way to choose max and mean. You don't need any analysis to choose max and mean from the finite number of values. So here's my candidates for the class 1. Now for the class 2, we need to do the analysis of the boundary. In this case, because boundary consists of 3 straight line segments, my analysis of the boundary will consist of 3 different parts, 3 different sub-analyses. And there's no any other way to do it. You have to do this 3 different steps, 3 different analyses. First, you take the B1 boundary, that's this vertical line segment. You parameterize that segment, that's the parametrization. It's one of the parametrizations, I guess the easiest one. Now you use this parametrization, you just take your function only on the boundary right in here. You end up with a function of one variable, and you see where this function has critical points, which are stationary points or the boundary points. Critical points where derivative is 0. Well, on the other hand, actually, for this function, you don't have to do that. This slide says, well, this slide just pictures the function. We know what kind of function is this. It's a cubic function. It's a parabola kind of shape. We know where the max, where the mean, right here at the endpoints. So you end up with 2 points in terms of t, 0 and 3. When you project them back onto the boundary of your original omega via this parametrization, you end up with 2 points on the boundary, 0, 3, and 0, 0. Your function value at those points, 0 and -27. So it's another 2 candidates, which came from this piece of a boundary, B1. You repeat this for every piece of a boundary. This is the analysis for the second piece of a boundary. It's a B2 piece, it's a horizontal piece. This is the simplest possible parametrization for this piece. You restrict your function on using this parametrization. That's my new function. It's another cubic, another graph. Even though yeah, it's another cubic, another graph, but my graph lives on this segment -3, 0. That's the range for the parameterization. Again, the max and mean for this restriction, it's the end. They will be the endpoints. And that, if you project it back, if you project this back with the parameterization to the boundary, you end up with another two candidates for the max and mean: 0, 0, and -3, 0. That's right. And the final piece, B3, this piece. Again, I'm getting this is the easiest parameterization you can come up with for this piece. You take your function on this parameterization, you sub in this parameterization into your function. That's a substitution. That's right, that's a substitution. At this stage, at this step, well, a few simplifications have been done. That's what you end up with. This is a quadratic function with the branches going down. You for this function, well, at this stage you can do either the analysis with the derivatives as like a one-dimensional analysis from the first year, or you can just use the properties of the parabola. Let's just see what the slide does. Slide does the analysis with the derivatives. Look at this. It takes this function g of t, which is a restriction of my f onto my parameterization. This function, now you have this sub problem. You have to find out the max and mean of this function over the domain. That's another global max, global mean problem, but with a dimension 1 less. Because originally you have two-dimensional problem, now you have one-dimensional problem. But the strategy is the same. You identify the stationary points, which are the points where derivative is 0. Here it is. It's a t equal -3 on 2. Plus the endpoints, 0 and -3, but the endpoints already, I mean, we come up with those points already in my previous analysis for B1 and B2, so that's why probably here it is not considered. So the only point of interest from this particular piece of a boundary is this point here in the middle of the boundary, -3 on 2, 3 on 2. And now we collected everything. All of the suspects for the max and mean, we found them through two stages: interior point via stationary via the gradient, and then the boundary, which by itself contains 3 different stages, because the boundary is a collection of 3 straight line segments. All of the suspects are here. The values of the function are here. We can see the max. The max happens here, -1, 1. That's the very first point we found via gradient, and the mean happens in the endpoints of my triangle, 1 here and 1 here, and the value of the mean is -27. And this is a complete analysis for the global max and global minimum of the function over the domain. If you have such a problem, that's one of the ways to solve it. Yeah. Sometimes for the second part of the analysis, for the boundary analysis, you can use another approach. We're going to discuss it later. But this is the first approach which works all the time. Again, I draw your attention to the fact that when you consider your function on the boundary, you sort of reduce the dimension of the problem. It was very clear in this last piece in the B3 analysis. You restricted your function onto the boundary. You ended up with a function of one variable across some domain, which is similar to my original problem, my f across the domain omega. It's just the dimension became less, and that's why you can use the analysis from the first year. If, for instance, you will have something like this in 3 dimensions, by considering your function on the boundary of the 3-dimensional domain, you will end up with a 2-dimensional problem, which by itself will have its own boundary. And then you will have another restriction. It will be 1-dimensional problem. So it will be actually double layer reduction. Yeah, it will. I'm not sure if there are any problems of this type with 3 variables in the tutorial set, but if there is, it will require from you a lot of discipline. Every individual step will be easy, but combining them in a coherent and logical presentation, it will require a lot of discipline from your mind. Right, and that's the end of the question. Right, now, the next part in this set of slides is these are the discussion of stationary points. So these are the points where gradient is 0. And we need to know how to classify them in the subclasses. And it is, well, the slide suggests the approach where we do this on examples first, and then we try to see from examples in general strategy or a general analysis. So here's the bunch of 8 examples. Every time if you do gradient for all of these 8 functions, if you compute gradient for all of these 8 functions at this particular point, the gradient will be 0. I show you it will be 0. I'm not going to do these computations. It's easy computation. You can do it on your own, which means that 0, 0 is a stationary point for each of those functions. And our job is to classify the stationary point into subclasses: local mean, local max, saddle point, and saddle point, 3 subclasses. So local mean, it means that this point is the one where the function is to take the minimum possible value across some neighborhood around it. Local max, respectively, its function dominates the area, some neighborhood around the origin. And saddle point, it means that near the origin, at any distance, no matter how close, you can find both the values lower and less and greater than the value at the origin. The value at the origin itself, by the way, is 0 all the time, right? Every function in this list at 0, 0 has value 0. Right. So the first 2 examples, you don't need to do any analysis to see that in the first example, the 0, 0 is mean, and the second example, 0, 0 is max, because sum of the squares is always positive number, always non-negative number, let me say it like that. If either of x or y is non-zero, then the value will be strictly positive, and that's why the origin takes the minimum possible value, not only locally, but globally as well, as a matter of fact. This function never takes negative values. And that's why 0, 0 is minimum. You don't need any analysis, any derivatives, or any other things. It's just direct property of the sum of the squares. It's never negative. And the same analysis go here. I mean, the same analysis applies here because just have extra negative here. And here's the graphs from, I presume it's from Maple, these graphs, which just supports this observation. So 0, 0 and 0, 0 on both occasions is minimum. This function, that's a graph from Maple, suggests it's a saddle point because near the origin you have either points greater than 0 or less than 0. Analytically, you support this observation from the Maple construction by doing something like this. You say, if I vanish y, my function takes the form x squared, which means just near the origin, if I keep y 0, my function always positive. Whereas if I vanish x, my function takes the form negative y squared, which means at the same time near the origin, if I keep x equals 0, my function takes negative values. So you see my function, which at the origin takes 0 value, yet near the origin along the y equals 0 direction, function stays positive. Along the x equals 0 direction, function stays negative. That's a clear case for saddle point. That's how you argue this analytically. Because it is not always so clear from the graph, even if you construct it with a Maple or GNU plot or anything else, whether it is a saddle point. You have to present the analytical justification for that. This is the example of how you can do it. As a matter of fact, later on we'll see even like a more streamlined way of doing this. This is the epsilon version of this. It just supports this idea that you can make this close. I mean, so you can choose this point, or you can choose these 2 points near the origin, one of them where the function positive and one of them where the function negative, as close to the origin as you wish. This as close as you wish, it sits here in this line. For all positive epsilons, no matter how small that epsilon is, you can make 2 choices. One of them like this, with y being 0, and deliver the point very close to origin, at distance, as a matter of fact, epsilon by 2, such that the function is positive at that point. And the second choice, again, as close as you wish, because you make your epsilon small, this point gets closer to the origin, where the function is negative. This is the same two lines. I mean, it's the same. These two lines, they justify the same statement, maybe a little bit with a little bit more details. And that's why 0, 0 is a stationary point which is neither max nor mean, and that is, it is a saddle point. That's all we need to say here. That's a third example. Another function. Again, the picture from Maple suggests it is a saddle point, but if I'd like to see this analytically, I need to show that near the origin, no matter how close I set the requirement for the closeness of the point, I can find both points where the function less than 0 value and more than 0, greater than 0 value. So this time, the good choice for the directions, one of them you see, is the bisectorial approach. If I choose this approach, y equal x, then along this direction, function takes positive values larger than the value of the function at the origin, 0. Function at the origin takes 0 value. Now, what will be the choice for some other direction which will give us enough evidence that the function also has negative values as close as we wish to the origin? Huh? Well, you have the slides, right? What's the point of holding this down? Yeah, it's another direction, it's another bisectorial in the second quadrant, second and the fourth quadrant, which delivers negative values. And again, we can bring this as close as we wish to the 0, 0 point. You have to remember that all the time. So you can convert this into the epsilon type lines, epsilon type arguments as in this slide. You can convert this into this type of arguments, these two choices, y equal x and y equal negative x. So 0, 0 is neither local max, local mean, it's a saddle point. Well, it's a good observation, actually. The observation says that you can sort of make this function, xy, look like function on the slide before, like this function, difference of two squares. Even though this time not we're taking the squares of x and y, we're taking of the squares of x plus y and x take y. See? You can do the arithmetic here, you can do the expansions, and you will realize that this is a true identity. This expression, even though it's longer, it is exactly xy. The point of this extra line is just to say that in this case, we can make this function look as the function before, x squared take y squared, if we make a linear substitution, right? If we call this x plus y a new variable, say x capital, if we call this x take y a new variable, y capital, it will be new system of coordinates. It's a linear substitution, new system of coordinates. And with respect to this new system of coordinates, my function xy is x squared take y squared, my previous function. Another two. X squared plus y4, it's a local mean. Again, you don't need any analysis to conclude that because it's a positive. This number, this expression always deliver positive value. Even though it's no longer symmetric, but still, square and in the fourth power, they're never negative. The only instance where they're negative when you take the origin itself, and that's why this is a mean. This one, it's a saddle point. Again, you can use the two different approaches. One, say, y equals 0 approach will deliver the positive values all the time, as close as you wish to the origin. X equals 0 approach will deliver negative values as close as you wish to the origin. Even though it's getting harder to spot on the graph itself, that's a saddle point. You have to do this analysis. Oh, another two. This function and this function by the graphs, by judging by the graphs, we have a suspicion that the first one is a saddle point, second one is a local mean. Oh, that's right. First one is the saddle point and the second one is a local mean. even though this time finding these directions of approach which will confirm our observation through Maple analytically, we need some method for that. Before, the choice for the approaches was relatively easy to guess. It was like the x equals 0, y equals 0. Bisectorials, we always check bisectorials because they are very frequent. Frequently, they help a lot. I mean, they help frequently. But here, finding these approaches, especially here, to confirm that this is a saddle point, look what sort of method we can use to find these approaches. Yeah, let's just see the method. So this function, we can make this function look like matrix multiplication, and that's a very good idea. It's a brilliant idea, as a matter of fact, and you have to remember this idea. It will help you in many examples, not only with the local max and min, but with some other examples as well. Look what the idea says. You can think of this function, even though the function itself doesn't suggest any matrices, any linear algebra, or anything like that. You can make this transition and convert this into the matrix expression. You can take a row vector with xy, you take a column vector, or column vector xy, and you plug in this matrix inside. If you do matrix multiplication here, you will end up with this value. I show you, that will be the one. But now look what we say. We're going to study this matrix which sits in between. We give a name to this matrix, H, and we do spectral analysis of this matrix, so we find eigenvalues and eigenvectors for that matrix. Here they are. I mean, a bit of a computation is skipped here because it's the first year stuff. So you can double check this. I'm sure the person who put these numbers in here, he double checked himself. So we can trust these numbers, hopefully. So if you do this analysis, we will find two eigenvalues, -2 and 4, two eigenvectors associated with that, 1, 1, -1, 1. So if we do this diagonalization process, which you used to do in the first year, we will come up with the matrix P. Columns are the eigenvectors, normalized, 1, 1/2. The inverse of this matrix, because this is the orthogonal matrix. I hope you remember what the orthogonal matrix is from the first year. The inverse for such matrix, if you want to find that, you can just take the transposition. Here it is. And that's my diagonalization. If I apply my P transpose and P to my H in this way, the result will be a diagonal matrix with these diagonal entries. If I take this, I need to ask you to make this mental exercise, because P transposed is the same as the P inverse. I can take these factors, P transpose and P, and move them on the other side. I can move them here and here. So P transposed from the left here, it will go as a left factor on the right-hand side as P, right? Because inverse for P transpose is P. And the P as a right factor, it will go on the right-hand side as another right factor, and that will be P transposed here. If you take this expression and plug this in here instead of H, and you make a substitution of this type, so introduce two new variables, x capital and y capital, look what's going to happen. So you see, well, actually, this mental exercise is done here, almost explicitly. So my H matrix, which was sitting in between row xy vector and column xy vector, little xy, it is replaced with the, well, it's actually done a little bit differently. So it's done the other way around. So it is suggested that we make a substitution, capital X, capital Y, which has this link to little x and little y, via P matrix. If you transpose the whole identity, that's how you end up with that sort of relation you will end up with for the row vectors. Now, my function was of this structure. Now, I make my substitution, little x and little y on both occasions, replaced with the capital X and capital Y through these relations. That's the replacement. The inner combination of matrices, that's the diagonalization thing. That's a diagonal D, look back here. It's a diagonal D. So it is just D. And now if you do multiplication of matrices with the capital X and capital Y, is your negative x squared plus positive y squared kind of saddle point. So, as a matter of fact, if you look back at this example, remember this example. In this example, this last line, you see what it did? With a linear transformation, with a linear substitution, we converted my example xy into this canonical example. Canonical example of a saddle point, x squared take y squared. And now this method via the eigenvalues and eigenvectors, it gives you the general idea, general strategy, how you can always convert an expression of this type into difference of squares, or as a matter of fact, sometimes it can be sum of squares, depending on because these coefficients, -2 and 4, they are nothing but the eigenvalues. If they ended up 2 positive eigenvalues, then you will have sum of the squares, but still, the method always will work and will always deliver the combination of squares, pure squares with no mixed product of this type. As long as you make this substitution, and that's a linear substitution, right? That's a P is a matrix with numerical coefficients. So this method will always allow you to convert the expression of this type, any homogeneous expression of the second order. It is a homogeneous expression of the second order because every term actually it's a second order term. Combined degrees is 2, x squared, xy, y squared. All of them second order terms. Into combination of pure squares. In this case, it's a saddle point because you see, you can find one approach when you vanish capital Y. You will find the approach which keeps the negative values if you keep the capital Y 0. On the other hand, if you keep the capital X 0, you will have the function always positive. That's why you have a saddle point in this case. That's why you have a saddle, and that's actually the explicit relation. If you just use this substitution, if you use the P matrix for that, this is the explicit relation between the capital X, capital XY, and the little xy. And so when I say when you approach to 0 and keep the capital X 0 in the little xy terms, it means you keep x plus y 0. So you approach bisectorially in the second and the fourth quadrant. And this is just a double check. Oh no, it's not a double check, it's just how your function looks in terms of the little x and little y. So if you sub in your capital X and capital Y with the expressions in terms of little x and little y, this is the form of the function you will have. So my original function, look at this. My original function here, I'll go back to my function. This original function, which had this mixed term, which is hard to analyze on the spot. It's hard to predict what's the direction of the approach you should use in order to control this mixed product term. We can convert this function into the sum of the pure squares, you see? The same function, but only pure squares are present. You can do the arithmetic, you can do the expansion in this expression. If you do that correctly, you will end up with the same original function. But it's not the point. The point is how to be able to find these pure square expressions corresponding to the original function. And it's very hard to come up with this from the top of your head most of the time. So it is a sort of like a, well, you know this method which we used to call extracting the perfect square method. Well, this is advanced version of the extracting the perfect square method. This time we extract the perfect square simultaneously with respect to x and y, not like x first, then y second. It's not going to work that way, actually. If you try one after the other, you won't be able to come up with this. You will need this spectral analysis, eigenvalues and eigenvectors, in order to do this completion of the square simultaneously. Right, so that was the first function. If you do the same analysis for the second function, let me just flick back to the functions, to the setting of the functions here. If you do the same analysis for the second function, You can do the same analysis for this function. Again, you can convert this expression into the matrix form. And on these slides, we do have these computations. Look at this. Yeah, that's the one. That's a choice of a matrix you have to make for the H. And now if you do the same spectral analysis, that's my H matrix, eigenvalues, eigenvectors. This by itself requires some effort. You know from your experience from the first year, finding eigenvalues and eigenvectors, it is a laborious task. It's not like, you can do it in a few lines, but still it's doable. And if you find them, and if you repeat what we've done for the other example, you will come up with these perfect squares, and squares only, and that's how it will be. And this time we have sum of the squares, and that's why at the point 0 we observe minimum, because when you have sum of the squares, canonical example, very first example today, it was the minimum point. It was a point of minimum, sorry. So if you analyze these two examples of the same method, you will see basically that you can always decide whether it is minimum, maximum, or saddle point by just knowing the eigenvalues. Eigenvectors, you need them all to know the approach, especially when you discuss the saddle points. They will give you the approach, positive and negative approach in case of a saddle point, but making a decision whether it is mean, max, or saddle point, it is purely based, this decision, it is purely based on the eigenvalues and actually only on the signs on the eigenvalues. Look back at my previous example, this example. The eigenvalues here, they were -2 and 4, one negative, one positive. When we did when we found these perfect squares, one negative, one positive. Because it comes from here, from the eigenvalues. Because the diagonal values here were eigenvalues, -2 and 4. Second analysis we did for this function, eigenvalues were 2 and 4, and we got 2 pluses, and here we got 2 pluses. So as a matter of fact, everything just linked to these eigenvalues, to the eigenvalues of the matrix H, which appears if you convert your homogeneous expression of the second order into the matrix form. Yeah, that's right. And that is what is probably is it the wrong file? All right, we can discuss the what's the time? Any questions? Yeah, right. We can do what's said on that slide. Why not? Right. So, well, I hope these two examples they convince you that. Well, eventually they will convince you. Maybe not today, but after a while, when you spend some time with this, they convince you that. Especially in case of these two examples, the key idea was this conversion of your function into a matrix form, and then analyzing the eigenvalue structure of the matrix appearing in the middle of this double matrix product. Now, the reason these two examples are considered is that you can see a similar effect actually for any function. Not specifically the function which has homogeneous structure, because these two functions are very specific, you see? It's a combination of square terms all the time. Here there's a mixed one, but still you have very limited amount of functions of this structure. X square, Y square, and middle term, and full stop. Well, if you have 3 variables, it will be X square, Y square, Z square, and 3 mixed ones, XY, YZ, and XZ. And that's it. So you don't have many functions of this type. So the analysis, even though it's a really good one, it's really just shows you like the connections with the first year. So far, it has a limited applicability to the homogeneous functions of the second order. Well, the slide which I was looking at a little puzzled, it's actually designed to show you that the same method can be adjusted to any function. Not specifically the function which has any polynomial or square or homogeneous structure. Look at the slide. And that is actually based on the Taylor expansion. So look at this. yesterday, it was yesterday, right? The day before, sorry. Day before, when we discussed with you the Taylor series expansions, we saw these terms which appear after the linear one. So when you do a Taylor series expansion for the function, and this time on this slide we do it for the function of two variables. When you do the expansion, there is like a function at the point term, then there's a linear term, gradient vector dot product with the increment vector, like this. Then there was a second term, third one. The structure of those terms we more or less discovered with you 2 days ago. What this slide claims is that the second term in that expansion we discovered 2 days ago, it has the structure. It has the structure of the same matrix product as we just experienced with the two examples on the previous slides. It is a product of the row vector of the increments, column vector of the increments, and some 2 by 2 matrix in the middle. If you re-examine the terms we discovered 2 days ago, you will see the structure there. And that actually opens this possibility to use this spectral analysis we use for homogeneous polynomials of second degree here for any function. Because you see this term is crossed over. You know why it crossed? Yes, it crossed because when you look at the stationary point, gradient is 0. That's the definition of the stationary point. So this term actually disappears for the stationary point. And so the behavior of the function, this is a constant term. It doesn't change anything. So the behavior of your function near AB, where x take A and y take B is small, the behavior of your function is totally controlled by this term given by the matrix product. All of the other terms, they said terms involving higher powers of x take A and y take B, they will be, if I use my language again, they will be infinitesimally small in comparison to this. So the behavior of these bracket terms, which are hidden here, they do not change, they don't really affect your function much. The main driver for the behavior is this piece, because this one is gone. If it was present, that's the main driver. That's the gradient. It shows you the direction of the highest ascent or quickest ascent, and the quickest descent if you go the opposite one. But at the stationary point, this one is gone. And this one becomes the main driver for the function around the AB point. And for this, we just discovered a very effective way to analyze it via spectral analysis. All we have to do for this matrix composed out of the second order derivatives, we need to do the eigenvalue, eigenvectors analysis and analyze how many pluses and how many minuses we have among the eigenvectors. And that's actually the actual idea of the whole analysis, the whole classification of the stationary points of function around the point. A function of two or multiple variables. You will be building this matrix consisting of the second order derivatives, and for that matrix you will be doing spectral analysis, eigenvalues and eigenvectors. For classification purposes, only the eigenvalues you need. If you need the approaches where the function stays negative, where the function stays positive, or in general if FAB is not 0, where the function is less than FAB, where the function is greater than FAB, for that you will need the eigenvectors. In case you look at the saddle point. So that's right. That's in this last sentence. It is said what I said before. The main driver for the behavior of your f of x around the AB point becomes the second term, because the first term disappears because it's a stationary point. Right. That's the same. This slide says. Basically, this slide says what I said before. Can the eigenvalues of H determine the behavior? Yes, they can. In fact, only the signs of the eigenvalues, they will determine the behavior of your function around the point AB, as long as the gradient term disappeared. This matrix becomes the main driver. The spectral analysis of this matrix will give you the classification max or mean. Let's just see what else there. Yeah. Well, this is just a definition. Just this matrix has a special name because of its importance for the classification. We need to give a name to this matrix. All of the examples before, they were about the function of two variables. In case you have function of three or more variables, the same ideas, they will work. And that's why in case of n variables, you will have a matrix n times n, square matrix, for which actually spectral analysis is not an easy business. Because if you have more than 3 columns, actually more than 2 columns already difficult, because to find eigenvalues, you need to solve the characteristic polynomial, which is the polynomial of degree n, and we don't have like a general way to do it, right? We don't know how to solve polynomial equations of n degree n. But it's not really a problem in this topic, because in this topic, probably most of the time it will be a function of 2 variables, or if it's a function of 3 variables, some solutions will be either suggested or will be clear. But anyway, Hessian matrix, that's the matrix of this structure. The importance of this matrix is that, I summarize this again for you. This matrix basically governs the behavior, drives the behavior of the function near every stationary point. Because near every stationary point, gradient disappears, and the second term in the Taylor expansion becomes important. And that's why we need to know the behavior of this matrix. I think we can wind up at this stage. There will be more examples tomorrow. Yeah, thank you. Thank you very much. Tomorrow will be more examples, but that's a good point to stop.